Section 3.1, Functions. We're going to be looking at a new topic here called functions, and it's pretty vocabulary heavy, so we're going to start by covering 4 important vocabulary words. We're going to start with something called a relation. A relation is a set of paired inputs and outputs. Paired means that they go together. So we have a little visual representation on the right. We're going to start with something that we're going to put into a kind of like a machine, and it will have some rules, something for us to solve or do, and then we get an output. And the input and output are paired. They go together. Now, a function is a special type of relation. A function is a relation in which each input is paired with exactly one output. That means that if you know what your input is, you'll know what your output is. You're not going to put in your input and get 2 different outputs. So a function is really just a nice behaving relation. The domain is a set of all the inputs. So the domain starts here, that's where we start. And then we go to the range, which is the set of all of the outputs. And so that's how we can kind of think about relations and then functions. But that's not too helpful unless we have an example. So let's look at an example of a relation. So the most obvious way to show a set of paired inputs and outputs is to use ordered pairs, where the input comes before the output. And so we have 1, 2, 3, 4, 5 ordered pairs here, and the 5 of them comprise a relation. Now, we don't know exactly what the rule is for the function or the relation every time. All I know is that if I have this point 2, 3, that means that an input of 2 comes in, does something, and leaves to an output of 3. That's what 2, 3 means. Similarly, 4, 5 would mean an input of 4, go into the function or the relation, and have an output of 5. And that would repeat for the final 3 points. So I can identify the domain and range of this relation. It's definitely a relation because it's a set of ordered pairs. All right, and that's kind of what we need for it to be a relation. But to be a function, I need to have each input paired with exactly one output. So I'm going to have to look at that in a second. I can start by looking at the domain to figure out the set of all the inputs. Well, that just happens to be the set of all the x values. All right, the domain is typically the x values. And when I write these down, I don't need to write them down in any particular order, but I'll write them down in a nice order here. 2 actually shows up twice, but I don't need to repeat it. I just have to write it once. 4 shows up, 6, and 7. And so in any order, that would be my domain. Once again, that's because 2, 4, 6, and 7 appear as 2, 4, 6, and 7 as the x values in my set of ordered pairs. 2 has already been used, so I don't need to repeat it. The range is very similar, but instead we're looking for the set of all outputs, which are also the y values. And once again, the order doesn't really matter, and I don't need to repeat anything, so I'm just going to have a 1, a 3, and a 5. And so you can see that comes from the 1, which shows up twice, the 3, and the 5, which also shows up twice. So that's where you get your domain and your range. Now the question is this a function? Well, it depends on, I guess I could mark up here that the range was the y's. I forgot to say that before, sorry about that. So whether or not it's a function depends on if this rule is satisfied. A function is a relation, this is, check, in which each input is paired with exactly one output. So there's a problem here. The 2 is an input. However, the 2 is paired with 2 different outputs, 3 and 5. that's going to tell me that this is not a function. I need to know that I'm going to have the same output if I have the same input. I have to have, if I have the same x, it has to have the same y. I can't have one x value with two different y's. So this is not a function. We're going to look at it again in a couple of different forms to see how we can confirm that. But that's the general idea. All right, so let's see functions in some other forms. So one thing I mentioned is that there's a few different ways that you can represent relations. One of them is just the list of ordered pairs. And so what I have here is the same list of ordered pairs from the previous page, which we know is not a function, but it's just a relation. But that's okay. We can still show it in other forms. And so what I'm going to do is I'm going to look at three other forms besides just a list of ordered pairs. The easiest one is probably the bottom left, which is the input-output table. Basically, all that we have to do there is write our ordered pairs next to each other or on top of each other, depending on our table setup. On top here I have my input, which is x, and the bottom I have my output, which is y. And so I just go point by point. 2 is my input, 3 is my output, 4 is my input, 5 is my output, and so on. Again, just like with before, the order doesn't matter. You can rearrange them, but the important thing is that these are the pairs. You know, I can't go 2, 2, 4, 6, 7, and 1, 1, 3, 5, 5. That would change the order too much here. So I have to make sure that I'm keeping it connected like an ordered pair. I've got 7, 1. I have to have 7 next to 1. So that's the easiest one. A mapping diagram is also pretty easy as well, actually. To start off, you just write down the domain and the range. And we're always going to start with our domain, which is our x. We're going to go to our range, which is our y. And so in our domain, again, don't repeat. We have 2, 4, 6, and 7. And now, in order to fill in the range, we're just going to look at the y coordinates. And again, don't repeat. And I was going to do it in the order that they're listed. 3, 5, 1. Now what you need to do is you need to show a map starting at your input in your domain and going to your range. By a map, we're just going to draw an arrow. So for the first point, which is 2, 3, that means I have to start at 2 and go to 3. I'm going to put an arrow to show me that's the direction that I went in. I'm going to repeat this for the other points as well. 4 goes to 5. 6 goes to 1. 2 also goes to 5. And 7 also goes to 1. And so that mapping diagram there shows me the exact same information as either my list of ordered pairs or the input-output table. And then finally, one last way we can look at it is by doing a graph. So what I can do is I can take each of my ordered pairs and plot them on the coordinate grid. So I'm just going to go to the point 2, 3. That's right 2, up 3. 4, 5 is right 4, up 5. 6, 1 is right 6, up 1. 2, 5 is right 2, up 5. And then 7, 1 is right 7, up 1. So I could plot the 5 points that I have on a coordinate grid as well. So there's all sorts of ways that we can show a relation. We could do on these if it happened to be a function as well. But that's what we're starting with. All right, let's talk about each of these diagrams now. So I've just cleaned up my diagrams a little bit, make it a little bit easier to read. And we talked in the first page about why this isn't a function. It was kind of hard to explain. Well, in any of these other setups, it actually might end up being easier to recognize. In the list of ordered pairs, the reason that this isn't a function is because 2 is used as an input for 2 different outputs, 3 and 5. So that's really what's causing most of the problem here. It's 2, 5, or 2, 3, excuse me, and 2, 5. That's why it's not a function. In the mapping diagram, we'll notice that the 2 has 2 arrows going away from it. These 2 arrows are our red flag here. We can't have the input of 2 with 2 different outputs going to 3 and to 5. So those 2 arrows tell me that it's a problem. In the input-output table, my 2 is repeated. And that's not a good sign, because once again, that means that I have the same input with 2 different outputs. Not okay. And then finally, on the graph, remember that my input is my x. And here I have 2 points that have the same x value, 2, 3 and 2, 5. Once again, by repeating it, it makes me run into some trouble. Now, a word of warning. There are going to be things that are in here that are going to make you think it's not a function. It's okay that 5 is the output for both 4 and 2, and that 1 is the output for both 6 and 7. It's okay to have 2 arrows go to the same number if it's 1 or if it's 5. It's okay to repeat the 1 and the 5, or to have the same y values of 5 and 1. And that's because that doesn't have to do with the definition of a function. The definition of a function means that each input has exactly one output, not the other way around. So you can start from 2 different locations and end up in the same place. That's okay. Now, this is really helpful when we start to talk about what this looks like graphically. Let's see what I mean by that. If you have the graph of a function, or a relation I should say, you can tell if it's a function by using what's called the vertical line test. If you can take any vertical line and intersect the graph of a relation at more than one point, it is not a function. I have 4 different graphs here. The first one is just a graph of a bunch of coordinate points. The others are curves or parts of lines that are really just collections of an infinite number of points. And so we can't list all those points, but everything on this curve, on these parts of lines, and on this somewhat of a circle-ish shape, are all perfectly valid as relations because they're all ordered pairs. Now what I can do is I can take the vertical lines that I've drawn here in yellow and move them across the graph to see if I'm ever going to hit the graph at more than one point. If so, it's not a function. So I'm going to move along, and I hit the graph once, still once, and right here I run into trouble. Here I hit the graph at 2 points, which tells me right away that this is not a function. When I take that same vertical line and move it across one of these curves, you'll notice that even though there's an infinite number of points, I'm never going to hit the curve more than once. All the time, I'm only hitting it at 1 point. It's going to continue forever and ever, but I'm never going to hit it more than once, so this is actually a function. Down to the circle, I have lots of things that tell me it's not a function. Right here, right at the edge, I'm only hitting it at 1 point. But everywhere else, I hit it at 2 points. Right here, right here. Keep on moving it. Right here, right here. I'm still hitting it at 2 until I come to the very edge, and then I'm hitting it at 1 again, just right at the very edge, until I hit it no more. But because I can draw even one line that would hit it at 2 different points, that is not going to be a function. Finally, the last one. This one can be a little tricky. You can see that on this section, I very clearly only hit the graph once at a time. To jump over this little area here, that's also going to be true on the left side. The interesting point comes right here. It's a little tough to see when I put the vertical line over it, so I'm just going to slide over. You'll notice that this circle is open, much like it was when we looked at inequalities. that means that I'm not including that point, just everything right up to it. So if I'm not including this point, and I am including this one, when I move my my vertical line over it, I'm only really hitting the graph at this point. I'm not hitting it here. That point doesn't count. So despite how it may look, this actually is indeed a function. They're all relations, but only the two on the right are functions. Now let's talk about their domain and range. Remember that the domain and range are just the collection of x values and y values, inputs and outputs within a relation. And so even though these two graphs on the left do not depict functions, they still have a domain and a range. The domain for the first one, the range for the first one, is just a matter of finding the coordinates. And so take a second and identify each of those coordinates, and then come back and check your work. All right, how'd you do? All right, so you can see that we have labeled all those points now. Hopefully you got them all right. And now for the domain, I'm just going to list all of my different x values that I have involved there. I have -2. I have -1. I have 1, 2, and 3. And that's just coming from the -2, -1, 1, 2, and 3. The range will be very similar, just looking at the y values only. It's the y values starting at the bottom. We've got -3, then -1, then 0, then 3. And that's what I have. I've got to get those there. I've got -3, -1, 0, and 3. I don't need to repeat either elements of the domain or the range. I'm good with just leaving it as it is. Now that's if we have points. If we have anything that's connected at all, anything like this here, or even like these, even where there's a little jump, or a circle, something that connects back to itself, we're going to be able to express our domain and range using often all real numbers or an inequality, sometimes a combined inequality. For the first example in the top right, I want to remember that these arrows mean that my graph is going to continue like this forever. This means that my graph is going to keep on going up and to the right forever. This arrow means down to the left forever. If it's going to continuously go to the left and to the right, eventually I'm going to cover the entire x-axis, which means my domain can be anything. It's going to be all real numbers because I can go to any x value. Similarly, because my arrow goes down and up forever, I'm going to cover the entire y-axis back and forth, which means my range is also all real numbers. It's not always the case, but if you have arrows, typically either the domain or the range will be all real numbers. More often than not, it's the domain. Sometimes it's both. Now, if we look at the circle down below, the domain and range are going to be different. They're not going to go on forever. It's actually a limited section here. And I want to be able to know how limited is it. Well, the domain is the x values. What x values are covered by the graph? The graph goes from here to here and underneath, starting at -3 and going up to 3. And its x values everywhere in between are covered, twice in fact. So to show this, I'm going to use a compound inequality. I'm going to say -3 is less than or equal to x, which is less than or equal to 3. That means my domain is all the x's between -3 and 3 inclusive. And that's because I can look at my graph and find a point that has every x value in between there. Range is going to be very similar, but it's about the y-axis. I can see that I'm kind of stuck in the same size space. And so I'm going to write the range the exact same way, except instead of x, I'm going to use y. So I have -3 is less than or equal to y, which is less than or equal to 3. And then finally, I have this last example here. The domain, again, remembers all the x's, and it seems like I've got everything covered because even at -1, I have a point at -1, even though this is empty. And I'm also having arrows that extend to the right and to the left forever. So my domain, which it often is actually going to be all real numbers. The range is not going to be all real numbers, though. These lines both go down forever. So there's a highest point that we can get to. And in this case, I'm going to use just a simple inequality. I'm going to say that my y values have to be below or less than or equal to 1. This is a y value of 1. I have the function somewhere, everywhere below that, but not anywhere above it. And so there you go. There's just 4 examples of how you could use the graphs to determine domain and range. I know this is a lot of material, but hopefully we're off to a good start and you're understanding it fairly well.